He's going to talk to us about security considerations for low-cost satellites. Don't even think about leaving early. We're going to be drawing for 2 more door prizes after Paul's presentation. So stick around for that in addition to Paul's great presentation.
All right. Good afternoon. I'm Paul Wood, and I'm with Southwest Research. I've got a couple of co-authors on this, Abe Garza, who's an expert in our cybersecurity area, and Robert Clark, who's a longtime software developer for flight software for these sorts of systems. And so we put together a presentation, talk a little bit about security considerations for small satellites. Hopefully I can keep you awake this afternoon. I see I must have done something to aggravate Ronnie because he put me last at the end of the day. So let's just get into it. So I'm going to talk a little bit about why do we care about this, and then jump into our attack surface analysis and the risk analysis that goes with that, talk about some mitigations and recommendations. So I do want to make clear at the outset that our focus is on the flight segment, so the ground segment is worthy of attention, but we don't want to talk about that here. There's a lot of people already working on ground system things. We kind of assume in part that for a lot of applications, these are shared resources and there's already a big security process in place for those. So we're going to talk about the flight segment. The other thing I should say is we're definitely focusing on small satellites, so we're not concerned with major, commercial or government operations. That's all worked out. There are big teams doing that. So instead, we're talking to those of you who are doing technology demonstrations or academic applications, that sort of thing. So why do we care? Is anybody concerned about security for your satellites? Maybe a few. So in fact, there have been documented instances of interference. So in 2008, the NASA Terra EOS was interfered with for several minutes on 2 separate occasions. And in this case, the analysts confirmed that all steps necessary to achieve command of the satellite were achieved. So this is an actual instance of a non-trivial satellite actually being interfered with. So it can happen. In the same time frame, this also occurred for the NASA Landsat 7. In this case, not all the steps were achieved to command the satellite, but all the same, this shows us that certainly there are people out there who are attempting to interfere with what we're doing. So as we're moving forward here, there have been dramatic changes in the past few decades in space. We have many more satellites, so that means there are many more opportunities for targets for people to look at to try to interfere with satellites. In addition, we're working on developing lower cost processes so that the effort that we're putting into satellites is lower. As a part of that, we're going to necessarily want to reduce our efforts in the area of security as well. But it's something that we should probably pay at least a little bit of attention to, and I hope I can convince you of that before I get through here. In addition, because this is now becoming much more common, we have a much larger group of people who are knowledgeable about satellites in general, and so an old paradigm that was never universally accepted but nonetheless sometimes mentioned is that, obscurity, because very few people were in the community, meant that the number of threats were lower. Well, now we have a lot more people working on these sorts of things, and so we have a lot more people who have at least some knowledge about the kind of systems we're building. So one reason we care is because we all want our activities to be successful. Unfortunately, not everyone wants us to be successful. So threats come from many different sources. Sometimes we get threats from within our own team. and other times we have threats from rivals. So I think we see these kinds of things all the time in the news where, some particular group has either had somebody within their own organization do something, or somebody from the outside has managed to do something. Think of all the things going on with, the stolen data, which leads right into our next version, which is criminals. So, yeah, you don't really want to run into these guys in a back alley, I don't think. We also have hacktivists. I've described them as flat earthers. They're convinced that your satellite is the one that's finally going to, show that their ideology is false. So they may not be enthusiastic about your latest satellite development. And then, of course, there's a whole world of possibilities. We live in a very fragmented world with a lot of different people with different goals. So there literally is a world of potential threats out there. So in addition, new threats are emerging all the time. The ease of interference is increasing, with the changes we've been seeing in communications and reduction in cost of electronics and so on. The kind of equipment and the kind of expertise that's necessary is just, increasing dramatically all the time. So to look at this, we did an attack surface analysis. For those of you who aren't familiar with security concerns, this is a well-established method to perform a security evaluation for a system. And the goal is to identify areas of potential vulnerability. So what is an attack surface? It is any physical or logical interface that an attacker can potentially use to gain read and write access to a system. So it doesn't definitely mean that you can, but it needs to be evaluated if it has the potential. So clearly, I think physical attack surfaces require physical access, but logical attack surfaces do not necessarily require that physical access. One of the challenges is that the logical landscapes are constantly changing. We have constantly changing protocols. We have constantly changing interfaces within our software world, new languages, new operating systems, new paradigms, and so we're starting to bring those things into space as well. So before we had a very structured environment, but now we're trying to use, off-the-shelf software for more things. We're trying to bring some off-the-shelf software into our satellites. We're trying to use technologies that were not previously used in space. So maybe we're trying to fly, something like Python or some other language that hasn't been traditionally associated with flight operations. So things are changing. Looking at physical attack surfaces, for most of what we're talking about here, that's probably not going to be a problem once you've been launched. However, we should go ahead and make the point of looking at things before we launch. And so there's just a few examples of some kinds of interfaces that might be worth taking a look at. So some logical attack surfaces are on board. We have weak application isolation and boundaries between different parts of the system. So as we try to use more of that commercial or open source software, we are setting ourselves up for systems that we don't really understand well. When we wrote all the code ourselves, we completely understood the provenance of it. We knew where it came from. We knew what was included with it, and we knew what the risks are. But if you're going to include some vision processing software that you found open source and you haven't had a chance to really vet it, who knows what's in there? So there's some risk there. In addition, we've had traditionally fairly flat architectures with unencrypted and completely accessible storage across the system, between applications, and even between the application and the system software. So that's another area of risk. More recently, I think it's becoming clear that the supply chain is at risk. So we recently heard some stories about some network communications infrastructure that had some supply chain problems where there were some sort of elements built into them that facilitated monitoring, and so that's a new kind of risk, and so that's part of this constantly changing environment. Another area is, of course, the RF interface. So that's obviously how we communicate to our satellite, and exploiting those communications protocols to gain access is how most adversaries will accomplish this. So this is sort of an idealized picture of the infrastructure that we have for networking and communications for our satellites. So let's see, there's even a pointer here. Okay, so so looking here at our satellite comms, we see things like jamming and eavesdropping, potential for replay attacks, unauthorized access, traffic analysis, and so on. So these are the kind of things we're going to talk about in a little bit more detail. So our risk analysis is going to examine the risks using a methodical approach. We will identify the threat actors, codify the likelihood and consequences or impact of an attack, analyze the risks from the perspective of the attack surface analysis, and then rank them. We'll identify some mitigations and then develop a plan to accomplish the mitigations to apply them. So going back to our list of threat actors, have a list here along with some of the motivations that they may have and the threat level and likelihood that we evaluated for ourselves for the kind of systems that we're thinking about here. So we're back to our insider threat, and so there may be somebody on your team whose ego was bruised. Perhaps you angered them in some way, and you had to kick them off the team, or give them some role that they thought they should have had a much more significant role. So there's a risk there. And then I think there's also the potential for financial risk. Perhaps some competing firm or whatever might have compromised them. So there's the insider threat. And I guess I would also comment that we consider that threat relatively high because it's they know about your system, and so they represent a potential risk that's pretty high. The likelihood is maybe medium, but it's not the lowest, we don't think, in the set. Of course, the second team is our rivals. They hope to gain some kind of competitive advantage. It might be financial. Maybe they don't want your technology demonstrator to be successful. They want theirs to be successful. So we ranked those threats as medium. They certainly know a bit about how these systems are put together. They know a bit about you as your competition, and they probably have the wherewithal to do it. So there's medium risk there as well. When we look to criminals, their main interest is financial gain, and quite frankly, your little technology demonstrator probably doesn't have a lot of credit card information on it, so they may not be very interested in that. So we think the threat level from criminals for the kinds of academic and technology demonstrator systems that we're thinking about is probably pretty low. So it's a low likelihood and a low threat level. Ideologically, did that not go? There we go. So on the ideological scale, again, we think the threat level is low because generally they don't have a tremendous amount of resources. But on the other hand, you may be doing something that they're fundamentally opposed to. So we evaluated that as a medium likelihood. And then finally, there's everybody else, the whole rest of the world. They are seeking some kind of political advantage or economic advantage, and the threat level is very high. They have huge resources at their disposal. However, they're probably not very interested in your academic project or in your minor technology demonstrator. If you were doing something for a government, that's a high profile, that would be different, but we're not really addressing that in this discussion. So For those of you who are familiar with this sort of thing, you may have seen a chart like this in the past, and this is one that relates the likelihood and consequence of these risks and how serious they are. So you can kind of see that, some combination of limited or very low, limited or negligible consequence together with a very low likelihood or a low likelihood, we're looking at a low scale. Then it starts to get interesting when we have a combination of, say, very high on one end and very limited on the other end. So those are kind of medium. And then finally, of course, when it's both very likely and potentially significant or catastrophic, those are very high. So looking at our attack surfaces, starting with our electronics, we think that the likelihood is very low. Most of the things that we seem to be hearing about are applicable to terrestrial systems. And so, for example, those devices that were recently reported to have compromised systems with add-ons that people didn't know anything about are potentially technology that would not even be used in a space application. Or if they were, they might be used in a different way. They wouldn't be, in our evaluation, able to be used in a way that would allow an attacker to really exploit them. That's not to say it couldn't change in the future, but right now, that's kind of our perception. Similarly, for denial of service, it's conceivable, and if that occurred, you could lose control of your satellite, and that would be a catastrophic thing. But we still think the consequence, the likelihood is very low because the environment probably doesn't facilitate your attacker actually being able to exploit it. On the software side, we have open source software, and again, we think the likelihood is fairly low that this could occur, but the consequences could be significant because you might not immediately know what's going on. You've used all this new open source software that you've never used in the past, and you were hoping to get some great benefits out of it, but now something's going horribly wrong, and you don't know where to maybe even look. So we think that the consequence could be significant because it might be difficult to track down what's going on. So that is a medium risk. For your custom flight software, we think the likelihood is low, but the consequence is also not as high. It's non-trivial, but it's probably not as bad because you know your own software. You're less likely to have confusion when it comes to something that's going wrong. So, however, when you look at the risk chart, that ends up coming up medium as well. That's one of the challenges with this sort of technique is a lot of things tend to have a low likelihood and a high consequence or the reverse, and the net result is very many things turn out to be medium, and it's really tricky to kind of manage the process here to get something so that things are differentiated. So we try to do that, but even so, that's kind of a limitation of the technique, and I've seen more than once where everything is medium and it's really hard to figure out what to address or what to definitely not address. Continuing with the risk analysis, there are a number of things in the RF area. So the first one is jamming, and it's not terribly hard to do. We think there are a lot of potential adversaries who have the ability to do that. The consequence would be significant, so the risk comes out to be medium. The second area is eavesdropping, so we think that's even higher. It should be very easy to listen to these kinds of systems. So, that technology is just getting easier all the time, but the consequence is probably limited, right? You're not processing sensitive data. You have, an academic goal or you have a technology demonstration goal. So even though it may occur, it may not be terribly important. Replay attacks could be possible, and if they occurred, somebody might be able to take control of your satellite or make it do something you didn't want it to do. So even though we think that these systems are not going to be terribly interesting to people who could do that, if they did it, the effect on your project would be significant. Similarly, if they actually completely took control of your satellite, that could be catastrophic because they could, put it into a mode where it could never be recovered again. So that would be bad. Traffic analysis, they could do that, and the consequence and the likelihood is maybe medium, but again, it's sort of like eavesdropping. It's like your data is not all that exciting, so maybe it's kind of limited in terms of consequence. And then finally, the data manipulation, we kind of perceive that as, again, a very low possibility, although the consequence could be significant. So what kind of mitigations should we consider for such small satellites? For the electronics, our risk rating that came out of the previous slides was low to medium, and the key vulnerability is counterfeit parts. So one of the things that we do with more critical systems is we do include security in the part selection, and some of that information is fairly readily available. So it seems even for our low-cost satellites that it would be prudent to make sure that there aren't any security bulletins or other items of warning out there. And in particular, I think we are going to be attracted to parts that are low cost. So I think there's a risk whenever you see something that's 10 times cheaper to say, well, great, I'll just use that. But it might be a red flag to say, maybe there's a reason it's 10 times cheaper. Oops. For our open source flight software, we rank that as medium, and there are known defects that are frequently published. There can be unknown features. There's also the potential for insider threat. The bottom line is similar to the security information for the electronics, determine if the open source software you're using has well-known defects so that you at least know that they're present, even if you decide to continue on at risk. In addition, there may be features that you don't need, so you probably accept that because you get a lot of benefit from it, but it does open up a bit of risk. For your custom software, we're primarily looking at the insider threat. Independent review is one way that you can help to keep track of that. All of these we think are relatively low cost, so they wouldn't be particularly burdensome to a small project. Not completely free, but if you have any security concerns at all, probably worthwhile. Looking at the RF world, it's a lot more complex. The rating came out to be medium for all of these, and there are a number of vulnerabilities, and they vary in terms of the cost of the mitigation and the complexity of the mitigation rather dramatically. So, jamming, for example, is probably going to have a high cost to mitigate, whereas eavesdropping may be, handled with some simple encryption to prevent casual snooping of your data. The others are kind of similar here. We see that there are simple things that you could do to potentially help prevent replay attacks or unauthorized access. One of the key things we see here is that encryption could be helpful in a lot of cases, and there's hardware now that can help on a lot of these processors. It's available. I don't think many are using it if they haven't already been doing a critical application, but it's something to think about doing. So what are our recommendations? Overall, pay attention to security during design. Make sure that your electronics and open source software don't have known security vulnerabilities. And if they do, then evaluate it and make sure that it's appropriate to use them in spite of those flaws. Use independent review to protect against insider threat, and of course it always helps preventing design flaws as well. Use low-cost methods to improve the security of the RF link. The encryption feature of modern space processors is something that can be fairly readily turned on and will have a modest impact on your development. So it's worth considering. And if you're not already using sequence numbering in your commanding, you should consider doing that as well. That's a very low-cost thing to do. The other thing, because we know you're not building a very complex system, we don't think it's worthwhile to spend effort on asymmetric threats. You know, you cannot protect against nation states cost effectively, and you shouldn't go down that path. Instead, you should balance your security efforts against your goals, including your operational time period. So if you're going to launch something that's going to last for a week, your concerns are way different than the one we just heard about a few minutes ago, which was up there for, you know, several years. So those considerations are different. In any case, you don't want your satellite to be the one that gets hacked. So thank you for your attention, and I'll take any questions.
So I think there's one attack surface that's worth considering, especially in the low-cost satellites. I mean, you talked about electronics as a counterfeit or electronics like that. But if you're putting together a system with off-the-shelf components, like on a SpaceWire or some sort of serial port network, that's another important place if you don't really understand the provenance of where that piece of electronics came from. And, you know, you could look at putting in special extra interface checks on devices like that if you're worried about those kind of things.
Sure.
So.
Yep.
The two examples you had early on were attacks while they were on flight, primarily taking over the command link. It seems like the more, I agree with your charts in terms of what likelihood amounts to, but do you have any historical comment on one of your developers getting in and screwing up your loads or something like this, in terms of maybe it didn't make it all the way to launch? But I would think that that is a place that has very easy access.
It's true, and I don't actually have an example of that occurring. People tend to try to keep things quiet, and so that's actually a problem in the security area. We're seeing that all the time now, right? Organizations are not wanting to admit that they've been hacked and their customer data has been revealed, and they delay for a long time. Mm-hmm. And so, although I think it's a real possibility, I'm not aware of a case where that's occurred for a satellite like this.
So one of the things, you know, obviously your presentation is focused on the, as you said, on the flight segment, but one of your slides made me think of something. I think it may have actually occurred. You talked about data manipulation and the sort of the hacktivists, the ideological groups. Even if they may not have the resources to, you know, perhaps some of them might, but if they don't, to sort of hack it online, I think the real vulnerability in that particular ideological area is on the ground databases, and I think this has occurred already because you have one ideology or the other or wants the data to show one thing or the other, and so sort of hacking and modifying, manipulating that data once it's on the ground systems. Just your presentation made me think, boy, the ground system scientific community really ought to probably start thinking heavily about security, because manipulation of that data, it seems like it would be a large target.
Right, and maybe that's something I should approach next year.
Mm-hmm. You seem to have expressed quite some concern about using open source software, and I was wondering if you don't use any open source software, do you think it's preferable to just like take an executable that's provided to you completely closed source by a company? And if so, how would one go ahead and audit that? Because it seems to me that open source software actually provides a lot of security benefits, because so many eyes have seen the code and so many eyes can see and audit the code.
So that's a legitimate perspective on it, and mostly I was just pointing out, I guess, the paradigm shift, in the sense that we're now depending on a much larger volume of code to do many different things that we didn't do before. And so we no longer can achieve all of our goals with writing it all ourselves. We recognize that. In the past, maybe we did use commercial software to do some of that, but I think the trend is towards using large volumes of open source software, and maybe the change in terms of commercial software isn't that, you know, products is not that great. So that's the reason I emphasize it. Not because I think there's necessarily, that there's certainly a challenge and a problem there in terms of also not knowing what's going on inside of those products. So they do have the same problem of you do not fully know them, and they have a lot of capabilities, and you may not know what they are.
Thank you.
All right.
Good. Thank you very
Thank you.
much.